my good screen, the big screen?
No, we don't see
I
it.
started sharing. No?
No, not yet.
Okay, so let me see. Is it okay now?
Yes, now we have your screen.
Okay. Okay. So I just checked with Narges about the time over there. It's apparently your lunchtime. I hope that these philosophical discussions at your lunchtime are not going to be boring for you. I have tried to put some examples, but at the end, I decided to hide a big chunk of the examples because I don't think I will have enough time to go through all of them. But I will be happy to take questions afterwards, after I hopefully manage to keep this short. I will take questions and maybe show you some of those examples because the scope of the discussion is very large and it's really hard for me to keep the talk within the scope. So if you get too bored, don't hesitate to raise your voice and raise your concern and let me know to turn the page and go to the next chapter. But I have some ideas how to entertain you, but there are some rather complicated things that we need to go through, and I would like to start from the problem. So let me see if I can turn the page. Okay. So first of all, I'm going to go through the problem. What is the question? Why should we even bother with the question of augmenting or enhancing computational design with, for instance, artificial intelligence? And then the most boring part and the lengthiest part is going to be about the framework that I'm proposing to think about using artificial intelligence in design or using any form of computational intelligence or any systematic process for that matter. And the part that I have hidden is going to be the lengthy part about intelligent design machines or different kinds of generative design processes. But I'm going to talk about it anyway, a little bit, at least at the beginning. And at the end, I'm going to give you a whole bunch of keywords about artificial intelligence and some of the topics that I find relevant and interesting. So these are the three topics in generative design about which I've recently written a book chapter together with two colleagues. I will introduce the book where this book chapter appeared. It's a very recent one about generative design from design optimization to design customization. The purpose of introducing these at the very beginning is to kind of disassociate this issue of computational intelligence uh, from the usual suspect, which is almost always design optimization. I want to advocate for this idea that computational design can have and does have other purposes than only optimization. So sometimes our purpose is actually not at all about optimization. Our purpose is customization, mass customization of design, which is very fundamentally different from optimization. And sometimes our purpose is actually about participatory design. So it's not necessarily about design optimization. However, for the topic of today and for the book chapter that I've written for the book that Narges is editing, I've mainly focused on the first type, which is about design optimization, because it was about performance-driven design. But just to give you this idea of a broader scope, the scope, in my opinion, is much bigger, and it covers also participatory design and design customization. But I won't be able to go through those within this supposedly short amount of time in your lunch break. So as I said, I will first start with the problem. And the reason I want to bother with the problem is that I'm honestly a little bit, how shall I say it diplomatically, annoyed with the buzz and the hype around the subject of artificial intelligence in social media as some kind of a panacea to all problems of our field, or some kind of deus ex machina, or I don't know what's the word for it. a solution to all problems before even we know what the problem is. So I think it's very important to first think a little bit about the problem. And I'm focusing on performance-driven design, but I'm not a fanatic about quantitative things. I also think that in addition to the obvious, very obvious environmental problems that our field is facing, and we should somehow all be, to some extent, embarrassed about it, we should also worry about the human factors, the disappearing human nature of cities in the world, and so on and so forth. But okay, first let's talk about quantities. There are some big quantities that we should be rather concerned about, and we should think about performance-driven design as maybe our main mission. And then next to that, I'm a very outspoken advocate of human factors and ergonomics and everything that has to do with the human side of architecture. But the quantitative side, the environmental side, has to be taken care of first, if we want to be taken seriously, that is, as a field. And so the biggest confusion that I've seen about artificial intelligence is that is in the term performance. So computer scientists use the term performance quite often in their endeavors in computational intelligence and artificial intelligence for speaking about performance of machines in mimicking human beings in performing some tasks. And they're constantly improving the performance of their machines in mimicking human beings. But performance for us means something completely different. It is supposedly related to the performance of buildings. And if you want to gain anything from artificial intelligence, it should be related to better performing buildings. And this is a quote from myself that my students have taken. In computational design, we have a big problem if we don't know what our problem is, right? And as you can see, the students have given a nickname to me, Pirouz the Preacher, because I preach a lot about these things. So these two words, I think I might repeat them 100 times. Choices and consequences are the motto of my way of looking at design. I think that if we want to do anything meaningful in terms of computational design with artificial intelligence, it should somehow be related to choices and consequences. So if our field has such a large impact, then it is somehow our responsibility, and it boils down to the choices that we make when designing buildings, and these choices have consequences. Sounds obvious, but I feel like I need to repeat this many, many times. So sorry about that. And maybe from a more specifically scientific point of view, we can start getting into the idea of computational design from a rather mathematical point of view as going back and forth between choices and consequences. So if we want to know exactly what's happening, we should start from choices and trace them to the consequences, and that is a scientific endeavor, fundamentally. But if you want to start from consequences and design something or make some decisions that end up having some acceptable consequences, that's a fundamentally different form of knowledge, so to say, and that is design knowledge, right? And that is exactly in the center of my attention. And this is a picture that after the first time I drew this, I had an aha moment, because it's a very simple picture, in my opinion. This is an observation that I gained from topology optimization as a form of generative design, where you have thousands of choices, small choices. Each of them individually is rather insignificant, but together they end up having a handful of consequences in terms of some measurable performance indicators. And so the first task in computational design, just understanding how exactly our choices end up having those consequences, that is even far from being trivial, right? And imagine the next task, which is starting from here and figuring out how should we make so many choices so as to have some desirable or acceptable consequences. By the way, please feel free to interrupt me. If you had any question or if something was unclear, please go ahead and ask me. And choices and consequences, etc., etc. And sometimes I have a feeling that our field is so much obsessed with designing something with a computer that there's no time for thinking about these responsibilities. So I want to remind myself and my audience that we have some very important reasons to think about problems. And namely that for a long, long time, people have been calling the kind of problems that we have in our field as wicked problems or ill-defined problems or ill-structured problems, because they have some peculiarities in the sense that they are difficult to formulate. There's usually no easy way to even evaluate what is a good solution to a design problem. And they're somehow unique, and sometimes we have this weird chicken and egg dilemmas and so on and so forth. But recently, we thought that it's time after 1970 something, where the idea of the wicked problem was put forward. We thought that it's time to revisit this very notion of wickedness and propose a framework to go about formulating problems more systematically. Understand what is complexity and what forms of complexity do we have to deal with in formulating design problems. And then we can have a more, let's say, civilized and progressive conversation about problem formulation in artificial intelligence. Namely, distinguishing the physical complexity, the multidimensional or spatial complexity, and the psychological or human complexity of decision making. Yeah. As I said, as I warned you, this is going to be a little bit philosophical and boring for your lunchtime, so apologies for that. But this hopefully brings it a little bit closer to what I'm going to mainly focus on. This framework known as the FBS framework, or Function Behavior Structure Framework, was a very illuminating piece in literature, in the design research literature, that drew my attention to this issue, to this fundamental issue of difficulty of designing. The difficulty of designing is that you are given some requirements, and from these design requirements, you formulate a function for something that you're going to build. And from that definition of a function, you are somehow expected to define a structure or a shape, let's say S, and that is your design, right? But when you think about performance-driven design, the behavior of this structure, behavior is another word for performance, by the way, the behavior that is inherent to that structure, the behavior of the structure, and the behavior that you expect from that structure, let's call the bottom part of this diagram the performance, becomes an issue. So the question is, how do we go from a description, a very abstract description of a function, to a very concrete description of a shape or a structure or a building? According to some researchers that I've quoted below, there's some kind of a logical leap or jumping from ideas to conclusions in design, which is very typical of designers, because they are trained to propose a solution before even they understand what the client wants, right? So as designers, we are trained to design, and sometimes just looking at the site, we start designing a building without even bothering with the question, because we have an idea, right? That's in the nature of our field. But in terms of consequences and choices and consequences, this cannot be very responsible, because as you most probably know, the decisions that you make at the very beginning of a design task, the conceptual phase of design, tend to have very significant consequences in terms of costs. The capital expenditure cost, the embodied energy in your building, or the operational expenditure, the energy consumption throughout the lifetime of the building, and so on and so forth, are all going to be affected by some very relatively simple decisions that you make at the beginning of a design process. So, okay, I hope that I can finish the chapter of the boring philosophical stuff, and I hope to have captured your attention for the importance of having a framework. Why do we need a framework for computational design and for utilizing artificial intelligence in design? If you ask me, very simply, because we need to formulate our problems, okay? But to make it a little bit more interesting, I will try to mimic the style of this brilliant TV presenter, Mr. James Burke, who used to conduct a TV series, which was one of my favorites. It's called Connections. You can still find it on YouTube. If you are into some old stuff, this is about history of science, the connections between things that appear to be somewhat unrelated to each other at first, and their importance in bringing about progress in science and technology and human life in a way. So some relatively unrelated things, or at least on the surface they're unrelated, have inspired this framework, the theory of games and economic behavior. The most important book is The Sciences of the Artificial from Herbert Alexander Simon, this gentleman in the middle of the picture. And the idea of the choice and consequences in agent-based models, and the keyword of generative science that I've borrowed from Professor Joshua Epstein, and some generative ideas from the generative grammars of Noam Chomsky, and so on and so forth. So these things are here to just give you a background. But from a mathematical point of view, there are some other things that are very directly related to generative sciences and generative design. And these are, of course, differential equations, the idea of mathematical modeling through partial differential equations, and stochastic processes, multi-agent systems, and the idea of computational simulation, for instance, through Markov chains, and diffusion processes. And diffusion processes are best understood through the so-called spectral graph theory, which is at the core of my mathematical areas of interest. So computational design in the field of architecture, engineering, and construction is obviously related to geometry, but geometry is not the only field in the only area of mathematics that is relevant to computational design. Topology analysis, functional analysis, probabilities, and did I mention topology? Topology, yes, of course, and linear algebra more than anything, and multivariate calculus are obviously relevant to computational design. And contrary to some hypes on the social media, artificial intelligence was not created in 2010 or 2015. It has a rather long history, starting from 1950s, 60s, and maybe the most important breakthrough for the rapid progress that we are observing nowadays is from 1974, the algorithm for backpropagation and training of neural networks but even before that, there were different sorts of artificial intelligence that are still relevant to the idea of augmented computational design or generative design, which are not very well known, unfortunately, these days, because they are from a different paradigm of artificial intelligence, the logical or the symbolic paradigm, or the field of expert systems from 1960s to 1980s and 1990s is the paradigm that I'm talking about. It's called logical AI or symbolic AI. It's not my cup of tea, by the way, but I'm just mentioning that other forms of artificial intelligence also exist. And It's very, very difficult to make such a picture, and I will probably regret that I've made this picture because people will point out two problems in this picture to me. But I've sketched this picture for at least 4 months and revised it many, many times. And this is the version that's sort of set up. So on the top, you have the symbolic AI, the old type of AI that I'm not talking about, but I just put it there in the background. And you have different forms of intelligence. And if you want to get a very quick view, you have, let's say, the physics-inspired intelligence coming from some ideas from physics, most probably from the ideas related to vibrations and diffusion processes, the spectral stuff that I just told you about. And you have bio-inspired intelligence or collective intelligence or related to multi-agent systems, games, and so on. To make it a little bit concrete, I'm going to show you two brief examples of augmentation of design with physics-inspired intelligence and bio-inspired intelligence or agent-based or gamified intelligence. This was an analytic task actually in the Groningen region of the Netherlands. It's a region where there's a lot of gas extraction happening, or actually they have stopped extracting gas because the gas extraction brought about so many little earthquakes, but the earthquakes are not comparable to earthquakes in earthquake-prone regions of the world, but the buildings in the region were not prepared, and there were so many damages and people lost their homes, etc. And I did this research together with one of my students, two students, to help a company, Arup, in providing some consultancy for the government and the gas company to help rebuild homes and assess the damages, etc. So the first project was that I'm going to show you is this one, which is automatic diagnosis and triage, or prioritization of urgencies and damages, urgencies related to the damages, for which we developed a machine learning algorithm which uses exactly the spectral graph theory that I mentioned before. The idea was that, well, at least the task was that given a point cloud taken from an airplane from the region, we wanted to be able to guess the structural typology of the buildings just by looking at the point cloud at the roof of the buildings. So obviously this was a machine learning task, but before getting into an end-to-end machine learning task, I proposed the idea to in a way listen to the sound of the sound or the frequency of vibration of these shapes from a mathematical point of view, in the same fashion as someone listening to the sound of some glass in the dark to figure out what could be the shape of this cup or glass, right? The idea is very old. The idea is this: can one hear the shape of a drum? Can you guess the shape of something from listening to its sound? And mathematically, this means that you can form something that is called a shape DNA for the object just by creating a shape and then getting the shape DNA. And it's a very low dimensional representation of a shape as a vector, with which you can hopefully more easily provide some recognizable vectors that can be classified into building structural typologies. And that was the idea, and it worked. So we formed these frequencies of vibration as some eigenvectors and eigenvalues, and then we formed the so-called shape DNA, which is a vector, and we augment this vector with some other numerical variables, and then we feed them into a machine learning algorithm, and the machine learning algorithm detects the classes. So this was one example, which was inspired by a physical intuition about the shapes. The second example is you could somehow call it bio-inspired intelligence. It was about developing a planning support system for helping the government in implementing solutions for the betterment of this region and for the what to do after the diagnosis of damage, how to help people rebuild their homes, etc. So we defined a game, a very abstract game, in which agents, which are the household owners, households and the owners of the houses which have been damaged, are encouraged or nudged towards making some decisions. The decisions are like this: should I upgrade? Should I demolish and rebuild? Should I move somewhere else and build somewhere else? Should I move and buy something else? So these are the actions of the agents, and the agents are put together in an agent-based model in which the agents are trying to minimize their regret. The regret of missing out on potentially better decisions or not doing something. And then the agents together make these decisions and revisit their decisions in an agent-based simulation game. And the government, the local government can play this game along with the agents and see how they might react to the proposed policy measures or incentives or policy instruments. So I cut this short, and I jump directly into the main idea of choices and consequences again. The idea of augmenting computational design processes with artificial intelligence, at least one of the most viable ideas, the way I see it, is to help with two main tasks. One task, which is non-trivial, is making an understandable map of how these decisions, these many decisions, lead to a few consequences of importance. As you can imagine, making an understandable map is not going to be easy, because we are going to have to reduce the dimensionality of this map. Out of these thousands of decisions, which ones are more important? Even if there are hundreds of decisions, even if there are tens of decisions, which ones are more important? There is a central example about this in the book chapter that is soon coming out. But here, I just need your imagination to imagine in any of the design tasks that you have previously dealt with, you have had to make so many decisions. Which of them are going to be the most influential on the outcomes of interest? Oh, a few outcomes of interest, like daylight, like energy consumption, potential energy consumption, and maybe embodied energy of the building, right? And so mapping is obviously a difficult task, but now imagine the difficulty of the other task, which is finding almost an inverse function, going back from consequences to the decisions. So imagine this: wouldn't it be nice if we could somehow aim at certain consequences, some levels of attainment of some performance indicators, and say, what could be a good design that would achieve such and such levels of indicators? What should be my decisions? And in a way, in mathematics, in robotics, and in computation, this is usually known as problem solving. Solving a problem usually is about figuring out all the decision variables so as to get to some outcomes. Ax equals b in linear algebra, for instance, right? But this is much more complicated, because this, if we conceive it as a function, if we imagine it as a function, as a machine, it's a machine with, let's say, 1,000 inputs and 3 outputs, right? So we can call this machine a function, a vector function called f of x being the decision variables, and O being a vector of outcomes of interest. right? So if this is a function, then the first important idea is how to approximate this function, because this function is probably so difficult. This is not going to be some x squared plus sine of x plus something. It's not going to be possible. Most probably, it's not going to be possible to write an analytic function and say, this is it, right? In many cases, this is not going to be possible. There are some cases in which this is possible. For instance, in topology optimization, this is exactly what we try to do. We try to write down an analytic function in terms of the decision variables to get to the outcomes of interest. But when it is not possible, then you can think of it in general as a very complex function, non-linear, most probably. And nevertheless, it's a function. And then once we conceptualize this as a function, then we can think of an inverse function. What can be the form of an inverse function that can get us from the inputs, this time being the outcomes of interest, to the outputs, which are now the decision variables. And I've explained this in the book chapter in much more mathematical detail, where you can see that even a linearized version of this is relatively complex, but actually very intuitive and straightforward in a sense, because it is somehow possible to find not the exact inverse, but some kind of a pseudo inverse in these processes. And that's exactly one of the main promises of AI, that it can firstly help us to approximate functions, such large and complex functions with artificial neural networks, for instance. The example that I'm introducing in the book chapter is a Bayesian belief network. And the other one is that once we have approximated such a function, we can invert the function, hopefully. This one is much more difficult, as you can imagine, inverting a function. And back to the idea of the function behavior structure, or the FBS framework, we can see that the main task of generative design in this sense can be to bridge this gap, to bridge this logical gap in design, and help us navigate this design space more systematically, start from the consequences that we want to achieve, and somehow step by step logically arrive at the conclusions. Maybe I can mention something here before I go forward. In the so-called diffusion processes, which are nowadays very, very popular, thanks to Midjourney and these kind of things, you have this idea somehow implemented already, that you go slowly into some latent space with low dimensions, and you do this gradually and slowly, and then you can invert the process, and gradually you can retrieve some results back, and you can generate designs. So this idea is exactly the cutting edge of artificial intelligence right now. The idea of growing a design. I found this on a deck of cards for creative professionals. It somehow sounds like an insult to our field, the field of architecture, but I think there's something very nice about this that we can learn from. It says justice, gardening, not architecture. It contrasts the idea of gardening with architecture exactly because of the logical leap. Because as architects, we are trained to think with a logical leap, to think always about, this is what I want to build. This is what I want to put there as an icon, right? We rarely start from the idea that this is something that can gradually be shaped. But a gardener thinks differently. The gardener plants something and observes and caters for the growth of something, right? So that's the essence of the idea of generative sciences. First, we try to understand how something grows. First, we try to understand how something can be simulated. If we can simulate it, if we can grow it, then that means we can understand it. And if we really understand how it is going to grow, then we can grow it in such a way as to achieve some desired results. That's the idea. And if we want to do this in the specific case of architecture, then first we need a framework. And I'm again going around some subjects to get to the main issue of the framework, but this is it. This is the framework in full. I'm going to share the slides afterwards, so don't worry about so many words. The idea is that, well, the logical leap was about jumping from a very abstract definition of a function to a very concrete definition of a shape or a structure. But if we do it gradually, if we do it step by step, if we discretize decisions, if we identify individual decisions that have to be made, then we can distinguish some steps in the so-called conceptual design, and it doesn't have to be a sketch on a napkin. It can be a much more structured process of going from a mass, some big decisions about how we're going to distribute the mass of a building, how we're going to distribute the zones in the building, how we're going to do the routing in the building, connect the different parts of the building, and how we are going to eventually, yes, package the building and shape it and form maybe something iconic out of it, right? But most so-called artistic processes start with the idea of the shape and they end with the idea of the shape. This is an attempt to go beyond the idea of just shaping a building. We're not sculptors. We are not just shaping a sculpture, right? We're supposed to configure it first and then shape it. Yeah. And of course, there's construction and some other things that in the process of forming, it's not just a shape, it's also about the segments of this shape this shape has to be built not as a monolithic, gigantic structure, but as something that is going to be composed of multiple pieces. And this idea of segmentation is also very important in the process. And then we can see that the problem of design is not a single problem. It's actually multiple sorts of different problems. We can distinguish a massing problem, a zoning problem, a routing problem, and yes, different sorts of forming problems like segmentation problems, etc. Then we can begin to have a more disciplined conversation about what is it that we are busy with in terms of design problems. And this is an example that I'm going to use to sort of remind ourselves as architects who want to claim an artistic dimension for our field, that even a very, very artistic field like music has a notation, and we don't have a notation for designing buildings in the 21st century. And the field of music has had a discrete notation for writing music since 15th century, right? So we are so much behind. And this discrete notation that I'm proposing for spatial designs is an attempt in that direction, that we need to have a vector to represent shapes. This is one of the first attempts for this. We can have a vector, first of all, with ones and zeros, determining what is there and what's not there, to represent the mass of an object. And this is a very small example, 16 voxels out of 27 in a 3 by 3 by 3, sort of like a Rubik's Cube. And the number of possibilities in this little cube is in the order of the number of stars in the Milky Way galaxy, right? And if this discreteness sort of bothers you, remember that music, even the kind of music that is played on the violin, is consisted of discrete notes, right? So the discreteness of the notation does not limit creativity or beauty or whatever. It's just a way to get into the formulation of problems. And all kinds of shapes can be modeled as discrete shapes. And this is one of the main advantages of discretizing shapes, because once you discretize shapes, then you can easily encode them into ones and zeros, and you can define games, design games. This is something that I have not discussed in the book chapter because it would explode the book chapter into two. But here I can talk about it a little bit. This game of Go was one of our main sources of inspiration for proposing this framework, which we call Go design, in exact reference to this game. Is a very spatial game in a way, in which the two opponents are claiming spatial regions. I have a very superficial understanding of this game, by the way. I have to admit, it's a very difficult game to play. And the thing that caught my attention was that this was one of the key examples of games that was very difficult for machines to play. And there was a breakthrough in playing this game with reinforcement learning against a very intelligent human being. And this was a breakthrough for AI. After beating humans in chess, beating humans in Go was much more difficult. KG was the human champion of this game Go, who was beaten by AlphaGo, a machine which had artificial intelligence in the form of reinforcement learning. The machine had just learned how to play the game. And the beautiful thing about this was that nobody had taught the machine all the possible strategies for the game. The machine had learned by playing. And this is the beautiful thing about games and about discretization of decision making, because the machine had only learned from the consequences. If I do such and such things, I will gain such and such points. Yeah. And therefore, the machine had learned the strategies, more or less like a human learning how to play. So we got this idea and we put it in the name of the framework, Go Design. And then we thought, okay, instead of proposing algorithms for design, maybe we can just propose a framework for formulating design problems, as planning problems, as configuring problems, and as shaping problems. I won't bore you with the details. The details are all in the paper. This is just a framework about how can you formulate your design problems. It's just about inputs and outputs, you know. So you might wonder what on earth is a framework. It's about naming inputs and outputs and understanding exactly how they relate to each other. The exact nature of the relations is something else that goes into the domain of problem solving. But first, the problem has to be formulated. For instance, this is a problem of configuring, I guess. Given a list of spaces S, a spatial quality criteria C, the actors are asked to reach a consensus on space. So this is a planning problem. So this is a generic form of a problem formulation that can be specified further in terms in a different context. So this was our attempt. So instead of proposing solutions, we wanted to propose a framework for defining problems. This one is the most difficult one, a configuring problem. Given a discrete envelope as a set of boxes V, the quality criteria functions F sub K, and the space properties P, the desired closeness ratings G, and spatial quality criteria weights W. It is desired to find a configuration X satisfying the local constraints as listed in P, the global constraints G sub P. These kind of things, right? And let me show you this in action. So this short animation shows the application of this framework in a course that we had for teaching computational intelligence for design. This was a course in which the students, bachelor students, by the way, they designed the buildings without drawing anything. So this was designed without any drawing. This was designing only by means of algorithms. And what I liked about the results that were achieved was that they were not totally alien buildings. Some of them were believable buildings that could have been designed by hand, but the whole process was procedural. So, and it was all in Python. Another example of the application of this framework in design is from another course called Earthy, Earth and Masonry Architecture through Generative Design, using a library that we have developed for discretization of design called Topogenesis. Again, in this course, every part of the decision-making process was discretized, and the class was focused on the idea of gamification, not only optimization and shape optimization and topology optimization, but gamification for participation in the process of design. This was about designing multiple sorts of buildings for a refugee camp to be built with earth. And I think this one is a hospital design from one of the groups of the students. The two other libraries that we used were Speckle and Compass. Okay, that's it. And this is the part where I close off the subject. So this is a very, very a wide range of topics, but if you remember a little bit about the 3 types of generative design processes that I mentioned at the beginning, topology optimization and shape optimization are very much about models of change. If we know how something changes, if we can analytically model it, then we can mathematically optimize it. And therefore, I call this kind of design model-driven. The kind of design processes in which games can help us formulate the problem are sort of control-driven, in which you can utilize reinforcement learning, like the Go design game. If you can formulate it as a game, it's fantastic because you can utilize reinforcement learning to train a machine to play the game and play the game with you. And the kind of artificial intelligence that I've focused on in the book chapter is this last one, the data-driven type, which is generative models that learn from data. Bayesian belief networks, or BBN, is the particular type that we have introduced in our book chapter. The idea is that if we want to have a systematic process for utilizing artificial intelligence in these kind of processes, we have to be very systematic in our data collection. We have to form these vectors of performance indicators and vectors of decision variables, and somehow try to relate them in terms of the functions that I described to you before. And yes, we're going to make some kind of a black box, but a black box that we are going to like very much, and it will be a very useful black box because we do this in cases where it is very difficult to do anything else. It is difficult to make an analytic model. It is difficult to make a game. It is difficult to do really anything else. And then a black box can be a valuable thing because it can help us mimic the behavior of a very, very complex system. And the case that we have mentioned in the book chapter is exactly about that. We have a very, very large example of a policy decision tool about energy efficient buildings for the government of the Netherlands, which we approximate as a black box. And we are doing this exactly to help policy analysts analyze their policies for subsidizing energy efficient building transitions in the Netherlands without bothering with the details of every individual building and every single design choice. And this one obviously also relates to diffusion processes, Markov chains, and manifold learning. All of these ideas are related to the spectral graph theory that I mentioned somewhere in the middle of this talk. And that's it. At the end, I have 2 rather provocative examples from nature-inspired intelligence. I myself, I'm more into physics-inspired intelligence, but these examples fascinate me, nevertheless. One is the slime mold, which is a creature that doesn't even have a brain or anything like a brain, but it behaves in such a way that it exhibits intelligence, emergent intelligence, collective intelligence. This is a very famous example. This creature is some kind of a mold that eats things like oat. It loves grains of oat. And in this example, the researchers have put grains of oat in the places of metro stations of the metropolitan region of Tokyo. And the slime mold has grown a shape that somehow resembles the actual metro network of Tokyo to reach to these grains of oat, which is unbelievable, right? So, and this other example is a very curious example of a so-called termites cathedral. These termites I think in the jungles of South America have built this gigantic structure. For their scale of life, this is gigantic. I think compared to a human, this is half the height of an average human, but for the scale of the life of termites, these little animals, this is huge. This is actually not even a cathedral. This is a skyscraper. This is almost a city inside the cathedral. And this is all achieved by collective intelligence of these relatively stupid animals, right? So together they achieve something that maybe a whole group of human engineers cannot achieve. So there's so much to learn from nature, and that's what I want to end with. And thank the students that have contributed to this. Thank you for your attention.
Thank
And
you.
I'm happy to take questions.
It was awesome, very informative. Do we have any questions from our students?